All right. So, the acid base sheet is due a week from today. The synthesis redo is due on Monday. Monday, I will hand your exams back to you. I know I keep being asked by that, but he seems excited for the prospect. Questions? All right. So last time we started chapter 21. I didn't tell you that necessarily. This is chemistry at the alpha position of a carbonyl. I did talk about that. So I'm just going to talk about acetone. Well, let's talk about what's the name of that compound? It is butanone. What? There's got to be something else with that. Two. There's a 2-butanone. So the ketones, the name is just going to be whatever the alkyl chain would be, number where the carbonyl is, only at the end of it. All right. So, all right, I haven't put that up. I'm going to erase it. 2-butanone can form. Well, what did I want to say first? 2-butanone has 2 alpha positions. All right, so the alpha position is defined as a carbon bonded to the carbonyl. And that's true for any carbonyl containing functional group, right? Aldehyde, ketone, carboxylic acid, amide, acid chloride, whatever. What do you suppose they call this one? That's beta. Greek life pays off. All right, so alpha, beta, gamma. That alphabet just works. Honestly, most that's kind of fallen out of favor. So we still call the alpha position the alpha position. It used to be you'd see papers where people are talking about the epsilon chemistry or something. It's kind of alpha, beta, gamma now, and then it's just whatever omega. We don't keep them out there. Omega would always be the end. So the pKa of the beta proton here is going to be like 50. The pKa of these two will be different, right? That CH and that CH are different. Methyl CH and a CH2 CH are different. But the pKa's are going to be pretty close. We'll talk a little bit more about how you might differentiate them here in a minute. The other thing, if you recall from, I don't know, I guess this, I don't remember when we did this. Right, you can make hydrates of carbonyl compounds. This is especially common for aldehydes and ketones. And the name of the hydrate would be 2-butanone hydrate. We wouldn't get, I'm sure, actually, there's probably an IUPAC way to name that. I have no idea what it would be, but. All right, we also have, which I haven't mentioned, if you dissolve this in water, and this is an equilibrium, obviously, you also have in this case 3 enols. All right, an enol is, I've mentioned these before, just a carbon-carbon double bond, alkene, bonded to an OH. And we can actually do an equilibrium between the enols and the hydrates as well. All right, so we can take either of the CH2 protons off. We can take any of the 3 CH3s off. It's an alkene, so you can have geometric isomers, right? Cis trans. So on the left, we've got the 2 methyl groups trans, 2 methyl groups cis. On the right, if we make the enol with the methyl, then we end up with disubstituted, but it doesn't have geometric isomers, right? It's There's no way to be cis or trans there. So let's get it together, kind of staring at me. So let's do draw the mechanism going from the enol on the right to the hydrate under acidic conditions. So H3O plus is going to have some water around it. All right, so it's acidic conditions. So you can't have strong bases. There's not going to be any hydroxide involved here, right? If you look at this, we're going to break a pi bond. We're going to add an OH. We're also going to add an H out here. So we have an H and an OH, that's water. So we're adding water across the double bond. This is, you guys did this mechanism in chapter 8. So this would be all right, we're going to protonate the double bond. We're going to use the strongest acid available. That's H3O plus, not H2O. Protonate. This gives us a really nice, so we add the H there. It gives us a really nice carbocation. It's tertiary. There's an oxygen on it, so there's a lone pair that can help stabilize that charge. We also get H2O out of that deal. H2O adds. Doesn't quite get us there. You put your charge in. H2O is going to take that H at the end. That gets us to the hydrate. All right, going from the hydrate to the enol, we would protonate. We get this intermediate. Water would leave. We get to here, right? Then we would just lose the proton. We'd lose that proton and make the double bond. Make sense? We can get back to. So for this back reaction to come back to the enol, the base would take this proton. What do I get? Complete that. What happens if water takes that proton? That's not the full mechanism, so something else has to happen. Yeah, you get back to the ketone, right? So these protons come here, and then this get it back to the ketone. All right, so you guys should play around with this. You should be able, under basic or acidic conditions at this point, to go from a ketone or an aldehyde to a hydrate and to an enol. Right, mechanistically, and this happens in water. It happens not in water. You don't get hydrate, obviously, if you're not in water. You get enol sort of in everything. If we took 1 trillion of these If I took a trillion 2-butanones, this is going to be 10 to the 12th minus, there might be at any given moment 20 enols and 10 hydrates. All right, so we'd have a trillion minus 30 ketones, we'd have a handful of enols and hydrates. It's going to turn out that that's enough, right? We've already seen this in the oxidation of aldehydes and ketones, right? So if that's an H, the hydrate oxidizes just like an alcohol does. And so you can take a primary alcohol and you can oxidize it all the way up to a carboxylic acid. Same thing, if you, under acidic conditions, we can get an enol that will do reactions. Okay, so if we have, sorry. Be a bit of a, this might be challenging. I'll give you a minute to think about it. What do you think the product of this is? I guess I should make the point over here, or the point I was trying to make that I implied but didn't explicitly say. For almost all carbonyl containing compounds, the carbonyl form is heavily common, heavily. All right, so give that reaction a try. What do you get if you take cyclohexanone and bromine? This reaction goes through an enol first.
So just Br2 or in there salt?
There's just Br2 in there. To start. Okay, so this was a hint, right? You get the enol out of it. That enol is actually quite electron rich. The alkene is electron rich. It's got 2 alkyl groups and an OH. That OH is an electron donor. So that double bond is electron rich. It will attack bromine like an alkene does. And we're going to end up with that. The whole mechanism, you end, right, well, let me draw out what you'd get. You'd get that. Markovnikov's rule says when you do an electrophilic addition to an alkene, you get the more stable carbocation. The more stable carbocation is the one next to the oxygen. What do I have to do? What's the mechanistic step to go from that cation up to the bromine? All right, so you just have to lose the, oh, sorry, go ahead. Yeah. Right, so we have a second bromide floating around here. That bromide is going to take the hydrogen. I see a lot of you guys, and this is okay as long as you recognize it's a resonance structure. A lot of people will take that H and put an O minus there and sort of have a C plus bonded to an O minus. As long as you then follow that out with, this is a resonance structure for the carbonyl, that's fine if that's the way you think about it mechanistically. But really, you just take this proton, the OH sigma bond turns into a CO pi bond. And there you go. If you do this, so this is usually one equivalent. This can be a pretty messy reaction. If you have two equivalents of bromine, they both go on the same side. And that has a little bit to do with enol stability. Like if you guys come back over here, look at the three enols that we drew at the beginning. Got three enols here. Which one of these enols is the most stable out? Which one's not? The one on the right is the least stable, right? It's di-substituted. Both of these are tri-substituted. Probably you have stuck in your head somewhere trans is more stable than cis. And that's true from a spatial thing, right? If you want the big groups trans to one another. Here, a methyl and an OH are almost the same size. They're not much different in size. A methyl is actually slightly larger. So this one on the left is the most stable, but by just a hair over this. If you come over here, like once we have one bromine on here, the most stable alkene we're going to be able to make is right here to be tetrasubstituted. Make it here, it's tri-substituted. Honestly, this is not a great reaction. All right, so the book talks about it. I want you to be able to work through that mechanism. I want you to be able to predict the product. But if you have to do this, if you have a lot of alpha protons, you can get a real complicated mixture of stuff. If you only had like one alpha proton, we'll see some compounds like that, then it works great, right? You just get the bromine in that one position, you're in good shape.
You need to be an acid to get the enol?
No, you need, it can self-catalyze itself. The rate to get the enols is a little faster. Like the rates in here, this is all thermodynamics where we just sort of equilibrium. The rates go up if there's acid around, the rates go up if there's base around. I should have drawn the other, right? The other product here is HBr. So this gets acidic and it speeds up. What happens? All right. Question. I'm going to erase a little bit. Okay, so that was, you can get an enol. Enols are important as you consider reactions. If you're ever working with carbonyl compounds and you get some weird product, you should always wonder if the enol might have been responsible, if the hydrate might have been responsible. But most of the chemistry of the alpha carbon, most of the chemistry of the alpha carbon of a carbonyl compound is done under basic conditions with an enolate. It's actually still a very widely used reaction. And so I'm going to just draw up what the actual aldol condensation is. So it's acetaldehyde, right? Aldehyde functional group. Aqueous hydroxide and water and heat. Right? Normally this would, you're in water, you're going to heat it. The easiest thing to do is just to boil it. You know what temperature it is. And the compound you get out of that is a compound called protonaldehyde. You don't have to know this name. but it has to do, like, that's not, crotonaldehyde is not the IUPAC name, right? The IUPAC name is gonna be something like two, so it'll be 2-butenal or but 2-enal. So the 2 tells us where the ene is, the alkene. 1, 2, 3, 4 carbons is butane. Alkenes at 2, and then Al is the name that we give for aldehydes. Right? Most of the time, you will almost never hear people talk about aldehydes with an IUPAC name. The name would be like benzaldehyde or acetaldehyde. Like we'll say the functional group. Yeah. So how did that happen? Anybody got any ideas on how this reaction happened? Let me do this for you, and I'll ask. So you've got this hopefully written down in your notes.
Has to be chilled.
Very good. You're at least figuring out what I'm thinking. So there have to be 2 acetaldehydes, right? You can't create atoms. So if we've got four atoms, or sorry, 4 carbons in the product, we have 2 carbons in the starting material. Like, we can't just like invent 2 more carbons. So there have to be 2 acetaldehydes. So I've numbered the acetaldehyde carbons. Number the carbons in the product. All right. So 2 of those carbons, you got to figure out which ones are which. The methyl is going to stay the methyl, right? So we get 1, 2, 1, 2. In the mechanism, we're going to turn carbon 2 of 1 acetaldehyde into a nucleophilic anion. That's going to attack the electrophilic carbon 1 of another molecule. We'll go through the mechanism in just a minute, but I did a little bit of this in class Monday. Talked about the acidity of the alpha proton. So if you have an aldehyde, right? So the alpha proton to an aldehyde, the pK is going to be somewhere around 17. If you have a ketone, so a proton alpha to a carbonyl ketone, 19 to 20-ish. If you have a proton alpha to an ester, like 22 to 24, you can even have an O- here, right? So if we started out with an OH, we had base. The base pulls that OH proton off. That's easy. If you have more base and a stronger base, you can pull off the CH proton, right? But that makes it even less acidic, so like 25 to 27. So again, that pKa is talking about that proton, alpha to the carbonyl. All right, so let's go through this first What do you think the first thing that happens in this mechanism is? Draw a reaction. We start with this. So conditions are what? They're basic. So we're going to make bases. Which one of these is a stronger base? Hydroxide is a stronger base, right? Hydroxide, a lot of electron density on that O. That is going to be our base. All right, so hydroxide is going to take this proton. We get an equilibrium with the enolate. And now we have two molecules of water, right? I'm going to stop drawing all the waters here in a minute. But when the hydroxide takes that proton, it becomes a water. This is technically a catalyzed reaction, so the hydroxide is catalyzed. I don't know if you remember the aldol you guys did it was last week, but in lab, like we just added a lot of base. All right. This equilibrium, again, the pKa of water is like 15.7. pKa of acetaldehyde is about 17. So it's roughly an order of magnitude difference. Little more. So at equilibrium, you might have 20 on the left and 1 on the right. But that one, like 5%, that's still, if you have a mole of stuff, that's a lot of molecules. And so then the next step, this is where we stitch the molecules together. So we make the enolate of one acetaldehyde, and then it attacks the neutral form of the other acetaldehyde. And again, this reaction is being driven because the enolate's a really strong base. So this is essentially a Grignard reaction. I'm drawing it as an enolate, but you can also think about it as a carbanion, right? So that carbon's negative, just like in a Grignard, an organolithium, the carbon bonded to magnesium is negative. So the enolate attacks the carbonyl. You can go from the enolate, you just have to remake the pi bond and then remake the CO pi bond and then have the CC pi bond attack. So draw what we get there, right? We're just putting two of these molecules together. Draw what those arrows get you. All right, I've drawn it up there if you want to have a look. We make a carbon-carbon bond. That's pretty cool. We make that between the alpha carbon of the enolate and the carbonyl carbon of the aldehyde. The next thing to happen, again, we've got water around. The O minus takes a proton from water. We get that. That alcohol and aldehyde is the addition product. So up to this point, it's called the aldol addition. And in fact, that compound itself is called aldol. The common name given to that compound is aldol, and that's how we have the reaction name. This works for a whole bunch of aldehydes, right? And as you can see, we're gonna do a more sophisticated version in a minute. So then how do we go from aldol to propanaldehyde?
The OH takes one of the hydrogens and the central carbon.
So it could, well, not from the center, it could just come back from here, right? Well,
Yeah,
no, sorry.
that's, yeah,
So if that OH takes, what's it gonna take a proton from again?
the like carbon in the middle, like between.
So the pKa for that isn't enough. The pKa here, again, if we come back over here, it's like 17. If the OH takes that proton, right, then you get a protonated alcohol. That's gonna have a pKa of like 0. So now that's like 17, 18 orders of magnitude difference. So we do take the middle proton. The other thing we get here is hydroxide. Right, so when the O minus takes the H, and again, we just want to make sure that we keep things basic. Right, so you had protonated that OH, that would be an acid, that would make it a strong acid. This. And one.
The alpha carbon more acidic than the alcohol.
Nope. So his question is, why does hydroxide take this proton and not that proton? Take that one, you just come back to here. And this all of this is reversible. So, and this is where you got to think about equilibrium. Okay, so again, this equilibrium here between the alkoxide, like an alkyl O minus and hydroxide, is essentially 1-to-1. I mean, it's like 40-60. It would be a landslide in an election, but in terms of chemical equilibria, there's basically a lot of both. All right, so this probably bounces back and forth here. And even here, though, this is like 20-1.
I'm just confused. So it is taking a proton or no? Like,
We do take that proton that OH doesn't do. Did you mean hydroxide? Sorry.
oh, okay.
No wonder. Yeah, you did confused. You looked irritated.
We
Um,
sound like you made it sound like it was wrong and then did what I said and then I got it confused.
yeah, no, it's all my idea. Everything, the whole universe. I thought you meant the OH, alcohol OH.
Oh,
So that's what I was explaining. I thought you were saying this because what, and we'll see this. One way to eliminate here would be to work the reaction up at this point, right? Stop at the aldol point, work the reaction up, isolate the alcohol, and then dump it into acid, do an acid catalyzed dehydration, right? That would be one way to get to the same compound. But this all happens in the same mix, right? So, and again, this kind of comes down, this is sort of now exam strategy. Like I have not written H3O plus, I have not written H plus anywhere in there. There are no acids present. So we go from acid aldehyde to protonaldehyde without ever introducing acid. Okay, so yeah, I'm sorry. I thought you were saying protonate the OH to turn it into a ligand. Not what I was saying. So we do absolutely hydroxide takes that one. We still have an alpha proton. Takes the alpha proton, and then what happens? How do we go from this enolate to the proton? You don't protonate the OH.
I don't know why, but I know the mechanism in lab, the electrons in the central carbon like push like make the OH a leaving group, but
You don't like it, do you?
no.
Yeah, negative charge here, make a pi bond, hydroxide leaves. That's it. Why do you guys not like that? I've tried. I don't know how well I do it. When we do SN2, SN1 chemistry in Orgo 1, I try never to say hydroxide's not a leaving. I probably do sometimes just because I get frustrated because students will make hydroxide be a leaving group. You can't say hydroxide's not a leaving. Hydroxide is never a leaving group in an SN2 reaction or an SN1 reaction, right? You don't have an alcohol just spontaneously hydroxide leaves. But there are plenty of reactions where hydroxide is a leaving group. Why can hydroxide be a leaving group in this reaction and not say in an SN2? Forget SN2. Why can it be a leaving group here? That is a big part of it. There's sort of two ways to look at this, why the hydroxide can be a leaving group. All right, we're in hydroxide. All right, hydroxide is around. So making hydroxide isn't making the whole mixture any less stable. The other thing is this enolate is a much stronger base than hydroxide. Not much. It's a stronger base than hydroxide. Right? So if you just view this equilibrium, right? So if you just view this equilibrium, and then think about what we've talked about with acid-base chemistry, the side that's favored is the side with the weaker base. All right, so for most nucleophiles in an SN2 reaction, kicking out hydroxide would be making a much stronger base. If the nucleophile is a stronger base than hydroxide, instead of kicking the OH out, it's going to take the proton. And again, I just said that actually happens here quite a bit. So here we have stronger base is enolate. And this is the weaker base. All right, so kind of the reason I was trying to push you guys toward that is because I knew you weren't going to like it. Like I've done this before. I know classes never like it when I point out that hydroxide is a leaving base or leaving group here. But in the Aldol condensation, hydroxide can be a leaving. Basically, anytime you can make a really strong base beta to the hydroxide, right? So now if you think about it like SN2 chemistry, that's alpha and that's beta. Here we make a really strong base, it can push hydroxide out because that's actually making a weaker base. Right, so if we run this reaction cold, I'm saying hydroxide can be a leaving group. It's still not a great leaving group, all right? This reaction requires some energy. So if we run this reaction hot, we'll kick hydroxide out, we'll get the double bond. If we run it cold, room temperature, right, 20 degrees, we'll get the aldol product, the addition product itself. Think about that reaction. I'm going to move some front. But what's the problem with this reaction? Sorry. Other than the fact that those of you by the window can't see it, what's the problem with this reaction? Will we get a reaction? Maybe I'm asking. Will just take acetaldehyde on the left. Will hydroxide react with acetaldehyde? Yeah, right. I just spent like 20 minutes telling you that. Will hydroxide react with propionaldehyde? Yeah. Can nucleophiles attack acetaldehyde? You can look at the other reaction if you want. Can nucleophiles attack acetaldehyde? Yes. Right? Can nucleophiles attack propionaldehyde? Yeah. So what's going to happen here is you're going to get a mess. Right? Either of these molecules can be turned into enolates. Right, let's just go ahead and do that. So we can get two enolates out of this mess. And I've been telling you, all along, these molecules are not alive. They're not, they're tiny little non-sentient things. So the acetaldehyde enolate has no idea. It just is going to react with an electrophile. It doesn't know which electrophile I want it to react with. So this enolate can react with either of these. The propionaldehyde enolate can react with either of these. Right? So this is going to be a mess, is what's going to happen. You're going to get 4 different products. 4 different condensation products. And that in roughly equal amounts. So this is not a useful reaction. A useful reaction needs to make mostly one thing. Like ideally, the reaction would make one product that all you have to do is like filter it off or rotovap it. You have the product. So, what would I need to do? Let's draw the 4 of them. So the first one would be, right, this is what we just made. Acetaldehyde enolate reacts with acetaldehyde. Gives this compound. We'd also get acetaldehyde enolate reacting with propionaldehyde. Right, propionaldehyde's got 3 carbons, acetaldehyde has 2, so this would be 1, 2, 3, 4, 5. We could have the propionaldehyde enolate react with propionaldehyde. All right, so if I just took propionaldehyde and I dumped in aqueous hydroxide like you guys did in lab last week, I'd get that compound. All right, it turns out, well, let me finish. Propionaldehyde can also react with the acetaldehyde enolate. Right, so still 5 carbons, 1, 2, 3 from the propionaldehyde, 1, 2 from the acetaldehyde. Like I said, I get all 5 of those in roughly equal amounts. I get protonaldehyde by taking acetaldehyde during the reaction. Protonaldehyde is dirt cheap because acetaldehyde's cheap, hydroxide's cheap. We can make this really easily. Whereas this compound, 2-methyl-2-pentanal. Also cheap because propionaldehyde's cheap and hydroxide's cheap. So 2-methyl. So the aldehyde carbon is going to be 1. That carbon is 2. It's got a methyl on it. 2-methyl. It's where the alkene starts. So 2-pentene. And then it's an aldehyde. So al. But these other 2, these are more expensive. These are harder to come by, right? Because you get them by mixing up 2 different aldehydes. I mix acetaldehyde and propionaldehyde, or propionaldehyde and acetaldehyde. So if I want to make let's say I want to make just that one. What do I have to do? Like, I'm not asking for I don't want chemical reagents. Conceptually, what would I have to do? No problem. Move some furniture. Yeah. Yeah. So if you look at this, to get that product that I circled is this enolate plus acetaldehyde. Right? There's no way to do that. If you come back over and look at this mechanism, I'm using hydroxide as a base, and we consider, right, hydroxide is this really strong base. It can't be a leaving group. Hydroxide is a base. This equilibrium actually favors the left. It favors hydroxide. So hydroxide is the weaker base compared to the enolate. So if I use hydroxide as a base, or methoxide or ethoxide, any of those bases that are sort of that strength, I'm never going to get all of this, right? So what I have to do is something called a directed aldol. And the base is going to be, so in this case, we want propionaldehyde. So first, I'm going to use this base called LDA, which you guys who studied for exam 2 will recognize. Like, I should have just given exam 3 right after that, because all the old exams you guys looked at. That'd be a fun class. I never lecture. We just do an exam every day. Be like training for a marathon by running to LA. All right. LDA is a really strong base. I'm going to show you what LDA here is in a minute, but I want you to like write down somewhere that you can see it. It's not mixed in with a whole bunch of other things. LDA is an extremely strong base. All right, so LDA looks like that is LDA. Lithium plus, that's the L, lithium. Diisopropyl, so 2 isopropyls coming off that nitrogen. Amide. AMIDE. All right, I hate this. I mean, I don't hate teaching this. I hate this. IUPAC, who has made rules, like seriously, they could probably fill Wake Downtown with paper, all the rules to name compounds. And yet, in this year of 2022, right, you guys know what an amide is, right? It's a carbonyl bonded to a nitrogen. That's an amide. Also an amide is like NH2 minus. So NaNH2, that's called sodium amide. So a nitrogen that's got 2 bonds to it and a negative charge, that is also called an amide. Yeah, you guys, don't kill the messenger. I did not make this rule. I know I'm the one close. Like, why do people kill the messenger? Because the messenger's there, right? Like, don't want to be a messenger, get killed, don't be the messenger. Here's the rule for nomenclature in this class. You guys don't have to know this, okay? You guys, if I say an amide, you draw a carbonyl with a nitrogen on it. Right? The functional group we just talked about in chapter 20. I'm just trying to tell you what lithium diisopropyl amide is. LDA, the A is an amide. Don't get confused and think that's the functional group. It's stupid. Okay, so what happens here? Well, I'm gonna finish drawing this. So then so we first treat with LDA. We treat with a full equivalent of LDA. This is not, and maybe even a slight excess, like 1.1 equivalents. Just a little bit more base. A little bit more base than we have aldehyde. And then in the second step, we add acetaldehyde. And then in the third step, we do a workup. This would be the reaction to get the aldol product. I'm going to take you through the mechanism of this. And then I'll tell you how to get to the alkene. Again, getting the alkene is pretty straightforward. All right, so LDA, the base is this negatively charged nitrogen, so not a neutral amine. You can use a neutral amine the same way we use hydroxide over in the first aldol we did, right? Neutral amines are pretty decent bases. They'll pull a proton off. You'll get a little bit of enolate that can then react. Here, this nitrogen takes the alpha proton. So that's going to make the enolate. And I haven't been talking about it, but this is the product of step one. I haven't been talking about it, but an enolate's negatively charged. It has to have a cation with it. It has to have a cation associated with it, right? So why do we use the LDA? Why do we use LDA instead of hydroxide? Think about pKa. We'll do pKa's again over here. pKa of the aldehyde is like 17. Anybody got an idea of what the pKa, the acid on the right side of this, the amine? You're thinking ammonium. All right, so this is the reason I ask. I want you guys to know what is the pKa of an ammonium, an NH bond. If that H is positive, the pKa is like 9. That nitrogen is neutral. All right, that is not an NH plus, that's just an NH. And the pKa of this is 33. So the equilibrium lies like 16 orders of magnitude to the right. That's more than one order of magnitude. And again, orders of magnitude, factors of 10. So basically, by treating with LDA, and then we usually do this, you'll see this written in a lot of times, minus 78 degrees. Minus 78 means we run it cold. All right, what I want you guys to know is we run it really cold, not like room temperature cold. Minus 78 is a convenient, if you ever dig into, if you find yourself in a library, a bunch of old copies of the Journal of Organic Chemistry, and your iPhone's dead, you can flip through those and you'll see minus 78 used over and over. There's nothing magic about minus 78, it's really cold. The way we get minus 78 is by pouring acetone over dry ice. It sets up an equilibrium at minus 78 degrees, right? If I pour water over water ice, I get an equilibrium at 0. If I have water ice in equilibrium with liquid water, whatever is in there is at 0 degrees. So if I have dry ice and acetone, it's at minus 78. So that's simple. We can, like, organic chemistry is really not rocket science. It's fucking chemistry. Okay. We get this as step one. And then what you would do to that solution, still at minus 78 degrees, is you would slowly add the aldehyde. Right, so now I have isolated the enolate of propionaldehyde, and now I can add to it an electrophile. You do this cold, and you make sure that the acid aldehyde that goes in sees a whole bunch of nucleophiles. And so there's not a lot of proton exchange. If you do this temperature, if you do this higher and if you set it up so that the acid aldehyde that goes in can see enolate, you'll get proton transfer and you'll wind up back here with a mixture. So step 2, right? Acid aldehyde. We get our aldol. Draw the product you get from that. And 15 notifications. Probably my roof came on. All right, so from the enolate, O minus makes the CO pi bond, carbon-carbon pi bond makes a carbon-carbon sigma bond to the electrophile carbonyl. If you want to think about this, I keep drawing it like an enolate. I'm going to try to mix it up a little more as we go forward and draw it as a C minus. Right? I could draw this with the carbonyl attached and the negative charge on carbon. It might be a little, it probably would be a little easier for you. It was for me. Right? If you see that it's carbon minus, remember that the carbon minus is being a nucleophile. All right, so if you draw that out, we get, remember, the new bond is going to go on the alpha carbon. Not at the end of the chain. It's going to go on the alpha carbon, and whatever the alpha carbon's bonded to just hangs down as a side chain. So if you want to number this, 1, 2, 3, 4, 5. This will be 1, 2, 3. 2 is going to bond to 4. 4 gets an O minus. Right, so that's the product of step 2. Step 3 is just a protonate. I don't know what I'm writing, sorry. That gets us our alcohol. And then this is what I was saying earlier. You can go from the alcohol to the alkene either via hydroxide or acid. So we could drop some acid in here, H3O plus, or concentrated acid, do an acid catalyzed dehydration. You could use aqueous hydroxide, and we get to there. So dehydrate. Usually you're going to do this with H plus and heat, some sort. Heat it up with some acid. All right, so this is called a directed aldol because we choose the enolate we're going to make, and then we choose the electrophile. You would never do this to make a dimer, right? If all I want to do is have acid aldehyde react with acid aldehyde, I can just take acid aldehyde, dissolve it in water, add like a flake of hydroxide and heat it up. Same for propionaldehyde, adding to itself. If I wanted to make the one in the upper right, I would reverse the aldehydes over here in my sequence. I would start with acid aldehyde. I would make the enolate. Then I would add propionaldehyde. Yeah. That's step 3. Step 3 is just aqueous workup. You guys remember lab from last week? Did you use LDA? You did not. We would not let you do that. So these really super strong bases, aside from eating through skin easily, have a tendency to burst into flame if they encounter air. So it's not quite bucket chemistry. You have to be a little careful with it. So you did not use LDA. You used hydroxide. I think it was hydroxide, right? I mean, I teach the lab, but so did you use the same aldehyde? No. What was the reaction you guys did last week? Acetone and what? Acetone is the ketone. Acetone and acetone and benzaldehyde, I heard. Did anybody use benzaldehyde? Use benzaldehyde? Yes. What did benzaldehyde smell like? Almonds. Benzaldehyde smells like almonds. You know why? There's benzaldehyde in almonds. Science is hard. That does not always work out. Smells are often smells and dyes. Okay, we're not quite done. I've started making jokes maybe a little too early. So smells and the color typically are really vanishingly small components, right? So if you smell, if you smell a nice odor and you're like, oh, I want to isolate that and like have a bucket of it, like it won't smell that way when you have a bucket of it. It often will smell worse. Same thing with a dye. Almost every dye that we use, right? Like we're all wearing colored stuff. Like there's probably like 1/10 of a milligram of blue dye in this shirt. All right, if you took this blue dye and like concentrated it, it would look black. Every dye would look black. It would just absorb everything. Same thing with smell. But sometimes it works out that you can actually smell. And then sometimes things don't smell that way. So there's a compound called isoamyl acetate, which is a small ester. Smells just like bananas. There's no isoamyl acetate in bananas. All right, so the reaction was this. And that's the only product you get. Why can we mix up, oh, sorry. Yeah, okay, now you know how it feels. All right, why does benzaldehyde not react with hydroxide? Why can we just dump it in there and not expect a whole bunch of different products? Yep. Yeah, so this H is not acidic. And there's no alpha carbon because there's no carbon on this side, right? The alpha carbon is here. The alpha carbon is there, and there's no hydrogen on that. There's no way to make an enolate for benzaldehyde. Okay, so now we don't have to do all that LDA stuff. We can just make the enolate of acetone and dump in the benzaldehyde. So yeah, so this happens. OH minus. Let's draw it as a C minus here. All right. Why does the acetone enolate not add to another molecule of acetone? Yeah. There's more steric hindrance. Acetone enolate will absolutely add into acetone. If we did this reaction the way I drew it, teaching moment, I screwed up. Right? I didn't draw benzaldehyde here. So imagine I'm in the lab and I'm in a hurry. I got an exam tomorrow. I got a paper due. I got a meeting. My roof just blew off. So I set my reaction up, acetone, aqueous hydroxide, and I leave. I don't put any benzaldehyde in. When I come back, acetone will absolutely have added to itself. But if you look at the nucleophilic attack, those are your two nucleophilic attacks. There's less steric hindrance around the aldehyde than there is around the ketone. And I know because it's benzaldehyde, you're like, there's this benzene ring and that's big. Benzene rings are flat. And what really matters is what's next to here. If you think about a nucleophile, it's got to come down and sit on top of that ketone or the carbonyl or come from the bottom. So like you can put all the fluff over here you want. Doesn't matter. On a ketone, right, you got a methyl, there's hydrogen sticking up, it's kind of three-dimensional, same thing on this side. The upshot is nucleophilic attack to an aldehyde is almost always faster than nucleophilic attack to a ketone. And that's why you can do this reaction pretty well. This is a really nice, like that's why we do it in teaching lab, right? You get this nice color. Why is this compound colored? Lots of conjugated double bonds, right? So we did that back in the aromatic, I don't know, feels like 12 years ago or so. We were 5. Anyway, we get a nice color out of that. That's always fun. Oh, yep. Why does this not, there's no electrophile,
Oh,
right? So we make a nucleophile. And then you could absolutely start doing electrophilic additions to this thing. We're gonna actually talk about other chemistry we do with this molecule in a bit. Right now, let's see what you learn. This is back in the, you remember the whole thing where I give these assignments, take them up, make sure your name's on it. I will look at them. Everybody that turns one in gets a point. Set it on this table when you're done and you can go, or you can go next door to the lab. I'm gonna stop recording it.